Alright, let's do some entropy example problems. I flip a coin 4 times. What are the odds that I get 1 heads and 3 tails? What are the odds that I get 2 heads and 2 tails? Using our standard definition of entropy, what is the entropy of the macrostate in which I get 1 heads and the macrostate in which I get 2 heads? Okay, so here are all of the possible microstates for my 4 coin tosses. Here's all the possible combinations I could get. Alright, I write them all down, and then I ask, what are the odds that I get 1 heads? Well, I look at these, there are 16 possible microstates. How many of them have 1 heads? 1, 2, 3, 4. Looks like that's it. So 4 for 1 head. Alright, so the probability then is just 4 out of the 16 possible random choices that are all equally possible. So it's just going to be 4/16, alright? And that is just 1/4, so 25%. 1/4 or 25%. So there's a 25% chance I get 1 head. Alright, what are the odds that I get 2 heads? Well, how many of them have 2 heads? Here's 1, 2, 3, 4, 5, 6. Looks like we have 6 have 2 heads. 6 have 2 heads. Alright, so the probability then is just going to be 6/16. Alright, that's going to be 3/8. Alright, that's my probability of getting 2 heads. Alright, now how would I find, well, before we go on to finding the entropy, that's a lot of different states, right? If I asked you to do 4 of these, 4 coin flips on the homework, you'd have to write down 16 possibilities, all right? If I asked you to do 10 coin flips, that would be a lot more, all right? In fact, the number of different combinations you get goes as 2 to the n. So if it's 16 for 4 coin flips, it would be 32 if I gave you 5, or 64 if I gave you 6 coin flips, right? And that's a real pain to write all of these down and figure out, how many of them have 1 heads or 2 heads, all right? So there's another way we can do this. We can say, look, the number of possible microstates is just 2 to the n, all right? How would I find out how many coin flips have 0 heads? Only one of them will have 0 heads, right? That one right there. All right, only one will have 0 heads. How many of them have 1 heads? Well, if I've got n particles, or n coin flips, I have n different choices for which one to be heads. All right, so the probability of 1 is just going to be n divided by 2 to the nth. All right, the probability of 0, that's just going to be, there's 1 state divided by 2 to the nth. There's only 1 state in which they're all tails, right? 1 microstate. So that's 1 out of 2 to the n's. What's the probability of 2 heads? All right, well, what you can do is you can say, well, I have n choices for my first one and n minus 1 choices for the second heads. All right. However, there's a problem here. Like if I looked at this and I said, look, if I were going to do 2, maybe I choose this one to be heads for my first one, and then I choose this one to be heads for my second choice. But what if I chose this one for my first choice and this one for my second choice? Those are 2 different ways of choosing, but they give me the same microstate. So I actually overcount by a factor of 2 because I could choose them in any order, all right? So the probability of 2 heads, there's this many microstates then that have 2 heads, so the probability would just be this divided by 2 to the nth, right? And in general, the probability of n heads, let's say k heads, is just number of flips factorial over number of flips minus k factorial times k factorial, all right? And if you look at the homework and the video for the Entropy 2, it'll talk more about that, all right? But the point is, if you think about it, you don't have to write down all the microstates all the time. All right, so if I use this technique, right, for 4 flips, the probability of 1 is just going to be 4/16. All right, that's what we found, 1/4. And the probability of 2 heads, we said, was going to be n times n minus 1/2 divided by 2 to the n. So this is going to be 2 times sorry, n is 4, right? So 4 times 3, so that's 12 divided by 2, that's 6. So 6 divided by 2 to the n is 16. So I got the same thing I got up there. All right. Now, so once I know the probability, how do I find the entropy? Well, remember the textbook definition of entropy, when I know the number of microstates, it's just K Boltzmann times the natural log of the number of microstates that realize that macrostate. So the entropy of having one head is just K Boltzmann times the natural log. And how many ways were there to get one head? We said 1/4 of the, sorry, I don't want the probability, I want the number of microstates. So the entropy of having one head is K Boltzmann times the logarithm of the number of microstates that had one head. And we said for 4 coin tosses, there were 4 different ways I could get one. All right? The entropy of having 2 heads is K Boltzmann times the natural logarithm of how many ways were there to get 6, or to get 2 heads when I flipped the coin 4 times? We decided there were 6 different ways. So there's the entropy. All right, so the entropy of 2 heads is greater than the entropy of 4 heads. The probability of getting 2 heads is greater than the probability of getting 1 head. All right, so higher entropy represents higher probability. Higher entropy means there are more microstates that describe that macrostate, and each of the microstates are equally probable. So if I've got more of them for a particular macrostate, I'm more likely to hit that particular macrostate. So higher entropy means higher probability. Okay, here's another problem. I drop a 100-gram cube of iron at a temperature of 80 degrees C into 100 grams of water at 25 degrees C. How much does the entropy of the system change as it reaches equilibrium? All right, so I'm given the mass of the iron, I'm given mass of water. I can look up in my textbook, I can find the specific heat of iron, the specific heat of water, right? And I'm given the initial temperature of the iron, and I'm given the initial temperature of the water. All right? So the first thing I need to do is I need to find the final temperature of my system. And the way that I do that is I do calorimetry, right? I say mass of iron, specific heat of iron, times the change in temperature of iron. That's how much heat flows into the iron. Now the iron is hotter than the water, so that heat is going to be negative. So negative heat flows into the iron. I add that to the heat that flows into the water, mass of the water, specific heat of water, T final, minus the initial temperature of the water. And the total heat flowing everywhere has to be 0, right? So this is positive heat flowing into the water. That heat is coming from the iron, so that's going to be a negative Q. Conservation of energy says they have to be the same, right? So I just solve this, right? And I say mass of the iron, specific heat of iron, plus mass of water, specific heat of water. All right, so I'm factoring out the 2 terms that have the final temperature in it, and I'll take the other stuff to the other side, which is mass iron, specific heat of iron, initial temperature of the iron, plus mass of the water, specific heat of the water, times the initial temperature of the water, right? And so I divide by this, and I find the final temperature. We've done this before, so I'm not going to go any further with that. But once we know the initial temperature of the water, the final temperature of the iron-water system, I want to find out how much the entropy of the system changes. Well, first let's find how much the entropy of the iron changes. All right, and remember we said that in the video, the entropy change of a solid or a liquid when heat flows in or out of it, it is just equal to the specific, or say the heat capacity of the object. For the iron, that's the mass of the iron times the specific heat of iron. So the heat capacity times the natural log of the difference in temperatures. All right, temperature final over temperature, initial temperature of the iron. All right. The change in entropy for the water is just going to be mass of water, specific heat of water, times the natural log of the final temperature divided by initial temperature of the water. So as the water approaches this temperature, the water is going to heat up. The final temperature will be greater than the initial temperature of the water. Its change in entropy will be positive, right? For the iron, the final temperature is lower than the initial temperature, so my natural logarithm will give me something negative. Its entropy goes down. Can the entropy of something go down? The entropy of a closed system cannot go down. But the iron is not a closed system. It is exchanging heat with the water, right? The iron-water system is a closed system, so the total change in entropy of the system, which is the change in entropy of the iron plus the total change in, or the change in entropy of the water, that cannot be negative, right? The closed system cannot be negative. And in fact, we discussed that for reversible processes, the change in entropy for a closed system is 0, because I have to be able to play the film backwards and also not have the entropy go down, all right? But this is not a reversible process. This is an irreversible process. If you played a video of this, you would be surprised to see water and iron in equilibrium, and suddenly the iron's getting hotter and the water's getting colder, right? So that's irreversible. For irreversible processes, we said that the change in entropy has to be positive, so we would expect that the change in entropy in iron, it's going to go down by less than the water goes up, so that when I add them together, my total change in entropy is going to be positive. So once again, I know how to find the final temperature using calorimetry. Once I know the final temperature, I just look, what is the change in entropy of the iron? What's the change in entropy of the water? Add them together to get the total change in entropy for my entire system. How much does the entropy of 100 grams of ice at 0 degrees C change when it melts to water at 0 degrees C? All right? We don't have a formula for this, but we have our standard, like, infinitesimal change in entropy is heat that flows in reversibly divided by T. Is this a reversible process, or do I need to find a reversible process to get it from the initial to the final state? All right? This is a reversible process. If you saw a video of ice freezing and ice melting, now the shape of the ice, let's put our ice in a container so we don't worry about the shape, right? That could go forwards or backwards, all right, depending on which way heat is flowing in or out of it. All right, so I just have to integrate this. So the total change in entropy is just the integral from 0 heat going in to all of the heat going in, dqr over T, all right? Well, the cool thing is, for this process, the temperature is constant, so that comes out of my integral, and it's just the integral of dqr from 0 to the total heat going in. So the change in entropy is just going to be 1 over temperature times the heat that I put in. But how much heat do I put in to melt 100 grams of ice? It's just the mass of the ice times the latent heat of fusion. Plug in my numbers, and I get my answer. Now wait a minute, temperature 0, right? I'm dividing by 0? No! Because we have to use temperature in Kelvin. This is not a temperature difference, so I need an absolute temperature. So this is going to be 1 over 273.15 Kelvin times mass of the ice times L. Notice, mass of the ice times L, that's a heat, right? That's an energy, that's in joules, and the units of entropy are joules per Kelvin, so my answer has the right units. That's good, all right? My answer is positive. Is that good? Well, yeah, my ice heat is flowing into it, so its entropy is going up. If I take water and freeze it to make ice, heat flows out and the entropy goes down. Water is a, quote, more ordered state. Sorry, ice is a more ordered state than water. Okay. A piston is filled with a diatomic gas. It has an initial volume, VI, an initial temperature, TI, and a pressure, P. Then I put heat into it, causing it to expand at constant pressure to a volume, V final. How much does the entropy of the gas change? All right, well, we've got our little equation here, right? ds is equal to dq reversible over T. So the change in entropy is just going to be the integral of dq reversible over T. So I just need to, from 0 to the total heat put in there, I just need to find some reversible way to get from my initial state to my final state, all right? We don't really need to do that because, as you recall, in the previous lecture video and in the homework, you will derive a general formula for the change in entropy for an ideal gas undergoing any process, reversible or irreversible, what have you, all right? And that turned out to be that the change in entropy was just NCV times the natural log of the final temperature over the initial temperature plus NR, natural log of the final volume divided by the initial volume. All right? Okay, so all we need to do is find N. How do I find N? PV is equal to nRT. I'm given the initial pressure, I'm given the initial volume, I'm given the initial temperature, so N is just going to be PV over RT. So I've got N. I've got N I can plug in here. What is CV? It's a diatomic gas, right? So a diatomic gas has generally 5 degrees of freedom. So this is going to be 5/2 R. I've got CV. All right, so I've got NCV. I've got NR. I've got my initial and my final volume. The only piece of the puzzle I don't have is the final temperature. I've got the initial temperature and I've got the final temperature. All right, but it's a constant pressure process, so I can use the ideal gas law. P V initial is equal to N R T initial. All right, P V final is equal to N R T final. If I divide these two equations, right? If this is equal to this and this is equal to this, then this divided by this ought to equal this divided by this, right? The pressures cancel because it's the same pressure, and I have V initial, V final. N and R cancel, T initial over T final. I can flip that, so T final over T initial is just V final over V initial. All right, so I have all the pieces that I need. So the change in entropy is N, but N was just PV over RT. And P initial, T initial, right? Because we know both of those. So P initial, T initial. And then CV was 5/2 R times the natural log of the ratio of my temperatures, right? But T final, V final over V final. T final over T initial is just V final over V initial, all right? And then this is just N, which is again P initial V over RT, right? It's N times R times the natural log of V final over V initial. So I look at this, the R's cancel out, and these are the same logarithm, so it looks like this whole thing is just going to be P initial V over T initial. It's an initial right there. All right, times 5/2, there's my 5/2, plus 1 natural log of V final over V initial, and there's my answer.